energy, energy upon which all life on Earth depends. Heat makes things move. Heat is a form of energy, like electrical energy, or chemical energy, or nuclear energy. All forms of energy can be sources of heat. But there's a special relationship between heat and kinetic energy, the energy of movement. When the movement of a basketball player, for instance, is stopped when his knee rubs against the floor, enough heat is produced to cause what's called a floor burn. Friction always produces heat because heat and kinetic energy are related. For example, a paper airplane flies slowly without much kinetic energy. There's some friction between the paper and the air it passes through. Not much, not enough for the plane to get significantly warmer as it flies. Compare this with the vast increase in temperature of a spacecraft as it re-enters the atmosphere at thousands of miles an hour. Now, friction with the air causes its outer surface to become intensely hot. Its protective tiles glow red. More friction, that is more motion, has produced more heat. Atomic theory offers an explanation for this connection. Every substance, of course, is made of tiny particles, atoms, ions, or molecules. In a liquid or a gas, like the atmosphere, these particles are not held together rigidly, so they move constantly in many directions. In a solid, like the tiles on a spacecraft, the particles are bound together into a solid structure. But they still move constantly, vibrating in place. Whatever its state, the more energetically a substance's particles move around, the hotter it is. And the less energetically they move, the colder a substance is. This suggests that heat is really a form of motion, or more specifically, that heat energy is a form of kinetic energy. That's why friction makes substances get hot. When things rub against each other, some of their kinetic energy is transferred to individual particles at their surfaces, making the particles move more rapidly, which is another way of saying that the substances gain heat energy. Kinetic energy is not the only form of energy that can be transformed into heat. When an electric current flows in a circuit, operating an appliance, for instance, the electrons that make up the current meet resistance to their flow from the material they're flowing through. When this happens, electrical energy is transformed into heat energy. This conversion of energy is put to work for safety purposes in a fuse. When current becomes dangerously high, enough heat is produced to melt a strip of metal in the fuse and break the circuit it's part of, and so prevent a fire or damage to the appliance. Chemical energy can also be transformed into heat. In a hot air balloon, when propane burns, chemical energy is converted to heat energy and put to work lifting the balloon. Our most important source of energy is the sun. Here, nuclear reactions release enormous amounts of energy, which are eventually transformed into heat. Nuclear reactions also take place much more slowly within our planet in the breakdown of radioactive elements, making a minor contribution to the heat that melts rock beneath the Earth's crust. Sometimes, when this magma breaks through the crust, it comes to the surface as molten lava. Nuclear, chemical, electrical, kinetic. In fact, every form of energy can be a source of heat. But there's an entirely different way for a substance to gain heat energy. Notice, The hot lava is heating the air directly above it. The air it's in contact with. This transfer of heat by contact is called conduction. Conduction also transfers heat within a single substance. Heat applied to one part of a metal rod is conducted to other parts of it and to other materials in contact with it. Conduction proceeds at different rates through different materials. Wooden handles never get as hot as the metal pots and pans they're part of because conduction proceeds faster through metals than through non-metals. And in airplane engines, the metal aluminum has a double advantage. Not only is it light, but it also conducts heat more quickly than most other metals. Molded into fins along an engine, the metal helps to cool the engine by conducting heat away from the cylinders and passing it harmlessly into the air. Aluminum is also a good conductor of electricity. In fact, most of the substances, like aluminum, that are good conductors of electricity also turn out to be the best conductors of heat. Atomic theory suggests that every solid conducts heat by passing vibrations along from particle to particle through its structure. But a metal that is a good electrical conductor has another characteristic. Some of its electrons are relatively free to move from one atom to another. So electrical conductors can also conduct heat by means of electrons that pass on their kinetic energy. A poor electrical conductor, like the air in our atmosphere, doesn't have free electrons to carry energy. It's an insulator. But what also makes air a good insulator is that its particles are so relatively far apart. These are also the reasons why air is useful for insulation against heat. Most insulation in the walls of houses is really a framework for many tiny pockets of air that help keep heat from being transferred out of the house in winter and into the house in summer. Air in the tiny bubbles of styrofoam prevents the heat of hot drinks from being transferred to your hand by conduction. Heat can also be transferred by currents of liquid or gas. This way of transferring heat is called convection. Glider flight depends on convection currents of air. A pilot looks for places where air is likely to be well heated by conduction. The best candidate is air over a large plowed field of dark soil bathed in sunlight. Here, solar energy enters the soil where some of it is transformed into heat energy. The dark soil of the field grows warm and warms the air above it more than air above fields with green plants are warmed. If green fields surround the dark plowed field, strong convection currents begin, rising streams of air. This is what the pilot wants, an updraft, a convection current of air that can lift the glider to a higher altitude as it slowly transfers heat to the cooler air around it. Convection transfers heat not only through the atmosphere, but also through the oceans of the world where currents distribute heat energy through the water. Convection currents even distribute heat in the sun. These flowing currents of higher and lower temperature produce the light and dark patches called granulation. But how does the sun's heat reach Earth? Neither conduction nor convection will work. Both require the movement of particles within substances to transfer heat. But there aren't enough particles in space to do the job. The sun's energy comes to us in a third way called radiation. This energy is transmitted in the form of electromagnetic waves. Unlike heat, electromagnetic energy can travel through a vacuum in the form of photons, tiny packets of energy. When photons strike an object on Earth, or the Earth itself, some of their energy is transformed into heat energy. Solar collectors make use of this heat energy radiated from the sun. All bodies in space, stars and dust clouds alike, radiate energy. The very hot objects give off high energy radiation, including enough visible light to photograph them by. But very low energy infrared radiation comes along with the light. Our atmosphere filters out nearly all of it, so objects that don't have enough energy to radiate light are invisible to us on Earth. But an infrared telescope in orbit, high above our atmosphere, gives us a whole new view of our universe. We've seen stars that have never been seen before, and clouds of matter in stellar orbits that may be the beginnings of planets. An exploding star, a supernova, gives off great energy. What remains of it may give off no light at all, only energy in the infrared. But an orbiting infrared telescope is sensitive to those radiations. The orbiting telescope passes on what its sensors have registered. And on Earth, we can see the infrared universe. While all bodies transfer radiation, they don't all do so at the same rate. For example, on a hot day, both the water in a lake and the land around it have received the same energy from the sun, but the land is warmer. Why? Because water absorbs heat energy more slowly than land does. But water also radiates heat more slowly than land. So at night, the water will be warmer than the land because the land has lost heat faster. The rate of heat absorption and radiation also depends not only on the type of substance, but also on a substance's surface. Some fires can radiate intense heat, but the shiny outer surfaces of these firefighters' suits reflect the radiation, absorbing very little of it. An object's surface area also affects the rate at which it radiates heat. A giraffe is a long, thin animal with a lot of body surface exposed to the air. So a giraffe's body radiates heat relatively quickly, an advantage for a big animal in a hot climate. But penguins live in cold climates. A penguin's body is short and stocky, with less surface area exposed that can radiate away precious heat. Even the mass of an object can affect its radiation. The penguin is very massive for a bird, and its body radiates heat relatively slowly. A hummingbird loses heat rapidly because of its small mass and high metabolism, so it must eat constantly just to maintain its body temperature. Some living things, like rattlesnakes, have special organs that can detect infrared radiation. In pits beneath each of a rattler's eyes are organs almost as sensitive to heat radiation as its eyes are to light. Even in the dark, the rattlesnake can find its living food. Humans also have ways of seeing in the infrared. The Earth looks like this in visible light. But with infrared-sensitive film, we can see heat variations that can give information about such things as crop diseases, heat loss in homes, and heat pollution in lakes and rivers. Across our planet, heat has its effects, visibly and invisibly, moving currents of wind and water, shaping and changing the world and its materials. While overhead, the sun bathes us in its radiance, bringing us the heat on which life itself depends.